Alright guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the component of velocity in two-dimension motion. And of course, this is going to be assisting us try to describe motion in two dimensions as we have been doing in our previous two videos. Now in this case, I'd like to, of course, request our members to subscribe. Check in our description boxes for various links of other similar videos which we have done, which I'm going to put there. So it's going to be in terms of playlist, and also check our social media pages for various other links which are going to be assisting us find discussions or topics under a similar discussion. So in this particular case, we're going to use these two specific illustrations, and we're going to consider motion in two dimensions, whereby we are going to consider an object moving in a circle about the origin. And in this case, I'm going to use these specific illustrations which I've given on the board in trying to do an analysis of this specific object. So this is going to be assisting us trying to represent the concept of velocity in two dimensions. And of course, that's going to be forming our final part of this specific discussion. Now, there are a range of ideas which we are going to borrow from our previous discussions under the concept of vectors and other related topics. Now, in this case, basically, it's going to be basically referring to the motion in two dimension or motion in a circle. And we have decided that for an object that is moving in a circle, we are going to see that it can be represented using this specific illustration, whereby we're going to have this particular object being shown above. So sorry for that. Let's consider this one to be an object moving in a circle in this specific direction. So the velocity component of this specific object is going to be tangential to this path of travel, as we have depicted from this specific illustration on our first case for A. So in this case, we're going to have the radius from which this specific object is moving given as r. And as we're going to see, this aspect of r basically is going to be a constant value which we are going to be using in our specific discussion. Now we can describe the motion of this particular object in two dimensions by using a two Cartesian coordinate system, whereby this is going to be formed using this, perhaps if I may use this one. So we're going to use the two Cartesian coordinate system in trying to illustrate the motion of this specific object, whereby at a particular point, if I may give, for instance, this particular point to be A and then the next to be B. So we're going to have this specific object move from the point A to B, and this is going to be resulting in an angular displacement given in terms of delta. So therefore, we can consider the velocity component of this specific object by considering the time interval it takes for a displacement from A to B, with the consideration of this angular displacement. Sorry for that. So this is going to be giving us the aspect of angular velocity, whereby we are going to have the angular velocity described by the displacement of this specific object from point A to B, given in terms of omega. So omega is equivalent to the angular displacement with respect to time, given as that one, whereby theta is going to be this specific angular displacement, and we can give the distance between A and B, which is of course our angular displacement given in terms of s. And of course, that's one of the ideas we are going to borrow in this particular case. But as we're going to see, using the Cartesian coordinate system for x and y, we can describe the various coordinates which are going to be, of course, described by that specific kind of a motion. And therefore, we are going to have the x component given in terms of this specific representation of the product over r, which have given us a constant, and the cosine of omega t. So in our representation of vectors, basically just given how we can represent this specific case from the trigonometric functions. And therefore, we are going to see that we can as well represent the concept of this displacement in the y coordinates by using the concept of sine, whereby we're going to have r sine omega t given as that one. So this is going to imply time, the angular displacement, the angular velocity, and of course this specific aspect of a radius. So in this both cases, we're going to see that this particular component of the radius, which we have given in terms of r in this case, and omega are going to be constant values, as I had just implicated from this specific statement, from my opening statement of this specific discussion. So we're going to consider this one to be just a constant values. And therefore, we can find the velocity component along the x and y by considering this specific respective displacement, whereby we're going to have this one given in terms of vx, which is a velocity component along the x, of course, axis given in terms of dx over dt. So that's a first derivative with respect to time, whereby we're going to have this x component given in terms of r, the cosine of omega t. So in this case, this is going to be given in terms of velocity component along the x is the first derivative with respect to time over r, the cosine over omega t. And this one, of course, from the laws of derivatives of cosine functions, we're going to see that the derivative of this specific component of course, the cosine is going to be giving us an aspect of a negative sign. And therefore, the velocity component along the x-axis is going to be given in terms of, so we're going to have this value in terms of r omega, the sine over omega t. So from the derivatives of trigonometric function, I hope that we're going to understand that one from this specific perspective, whereby we're going to have this specific aspect of omega and r being constants, and therefore we're going to have this negative value. So the derivative of the cosine function is going to be negative sign, and this is why we're going to have this specific negative sign given as such. So this is how we can represent the velocity along the x component for this specific motion in a circular motion. And similarly, we can have this specific component represented in terms of this specific aspect of the y component given as that one. So in this case, this specific triangle is going to be giving us the first motion from the point of this along x-axis to A to B, going in that specific order. And in this case, we'll be considering the angular displacement as we go along the way. So in this case, for the y components for the velocity, we're going to have the displacement along the y against the time, which basically implies that we're going to have a day of the value of y given as r, the sine over omega t, and this is with respect to time. So in this case, the derivative of the sine function is going to be positive cosine, whereby we're going to have this element of rw, the cosine over omega t, giving us the velocity component along the y-axis given as that one. So for us to find the resulting velocity component for these two specific displacements along the x and y, we're going to add these two specific components as we have been doing from our previous videos. Now, they indicated that suppose we have a displacement for a and b, we're going to have which are going to result in a vector c. We're going to have an addition of these two specific components in order for us to find the total of course, a velocity which is going to be implicated by these two specific aspects which I've shown for x and y. And in this case, we're going to consider a specific illustration whereby we have said that this specific speed and, of course, r are going to be constant. We can basically show that the speed is constant with respect to time by using this specific aspect of, so I said wherever these specific components are going to be interacting for the x and y, of course, they are going to be giving us this specific aspect of a right triangle, and therefore we can employ the concept of a Pythagoras theorem in trying to find that specific component of velocity. So in this case, I'm going to use this specific concept, whereby we're going to use the second case, whereby we're going to have the velocity component, the square of that one, given in terms from Pythagoras theorem, that is going to be vx, the square of that, plus vy, the square of that, given as such. So in this case, from the representation, going to give this one at this specific end. But we have said that basically the velocity component for the, of course, x is going to be given as vx is equivalent to negative r omega, the sine over omega. So space. So it's vx is equivalent to negative r omega, the sine of omega t. And of course, vy is equivalent, so these are vector components, r omega, the cosine over omega t, given as that one. So in this case, we're going to just do an evaluation for these two respective components which we have given in terms of these representations. So perhaps I can increase this one space for that one. So we're going to have the velocity component, the square of that one given in terms of the square of the v component, which is a negative r omega, the sine over omega t. And then we're going to have the r omega, the cosine over omega t. So this is going to assist us basically illustrate that these two specific components for r and angular velocity are going to be a constant component. So in this case, this is going to be giving us the square over r, and then we're going to have the square of omega, and then the sine of the square of omega t plus the square of r, the square of omega, the cosine square over omega t. And this is going to be giving us the square of that. So we can have this one given in terms of, we take these two specific elements which are constant vectors out, and then we're going to have omega t plus the cosine square of omega t given as that one. So from our description of our trigonometric function, this is an identity which is going to give us the value of 1. So implying that we are going to have the square of v equivalent to r squared omega squared. So further implying that v is equivalent to r omega. So therefore the velocity component of this specific kind of a motion is going to be, or the speed is going to be giving us a constant value with respect to time given in terms of r omega given as that one. So in this case, this is going to be a description of an object moving in a circle about the origin. And of course, considering its various coordinates for x and y, of course, we're going to see that we can, of course, illustrate its velocity components using the particular analysis which we have done in this specific video. So kindly check out description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell to be getting various updates on our uploads in math and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.